All right, so what I thought we would do, and I didn't exactly follow this lesson plan. I want to look at the code in just the first half of the lecture itself is a lot to swallow. So I thought I would just go through that code piece by piece until we get to the end of the notebook, of the third notebook. Okay, so I'm just going to go through that. I'm going to do it differently. Last time I just sort of blitzed through the notebook and executed every cell and showed that, and we talked a little bit about some of the cells. This time I'm going to look at the notebook 3A, the notebook, what's it called, mini batch, 03_mini batch. I'm going to look at the code cell by cell, and we'll understand what every cell does, hopefully. So let's get started. And here's what happens. He's basically building a training loop, and he gets that done very quickly, right? But the rest of the lesson is progressively refactoring it and making it nicer and nicer, making it more generalizable for later use. And the whole thing becomes very readable and compact, and there's very little wasted code. So he's making building blocks and then putting them all together at the end to get this training loop that functions the same way as he got it originally, but much more extensible. Now we can use this, we can go forward and use this again and again and again in different, and modify it and so on. And that's what we'll be doing in the next one, in the next notebook, 04_callback. Okay. And I want to make sure, I like to have interaction when I teach. So if there's any questions, just go ahead and jump in. If people are jumping in too much, I'll tell you. But I'm happy to stop and explain things if people are having, if my explanations aren't getting through to you. Just stop, make me stop, ask a question, and I'll try again. Okay. So with that, let's move on. So here's the overview of the whole thing. We have there's 4 steps. This is basically stolen from Jeremy's lecture. We input the training data. We have a model that we use. There's a loss function that goes along with that model. So we first run the model on the training data. We compute the loss function, and that's called a forward pass. The next step is backpropagation to compute the gradients of the loss function with respect to all the parameters. And remember, the parameters are the weights and the biases. And once we have the gradients, we can then update the weights and biases using stochastic gradient descent or some other technique or some variant of stochastic descent and so on. We use that to compute the step size. We update the weights and biases with that step multiplied by the learning rate. And once we've updated all the parameters, we then run the model again on the updated. We run the model again with the updated parameters, and then we do this as a loop. We keep doing it until we decide it's okay that we're converging, that we have a good metric, and then we stop. So that's the training loop. And once again, here's another view of it. I stole this from a Fast.ai student, Pierre Owanes, who wrote a blog post on this, and I just stole this slide from his blog post and I sort of modified it a bit. So you can see the first step, you start with the model. The forward pass computes the loss. The backward pass computes the gradients. And then we have an update. We compute an update for the weights and biases using an optimizer, which generally is stochastic gradient descent or one of its variants. And the next thing, once we've computed that step, we then update the parameters by adding the step times the learning rate. And then we run the model again, and so it's a loop until we decide that we're happy with our metric, performance metric, whatever that is. Okay, so now let's get into this. He constructs the training loop right away. So this is the functioning training loop. It's all done. It works. But the whole rest of this part of the lecture is just improving this. So let's go through and see piece by piece what's going on here. We are going to the inputs to this. We're going to fit the model, and the input is going to be the model, the loss function, whatever we decided it is, the number of epochs. That's this. The batch size. So epochs could be 1, or it could be 5, or it could be 2. An epoch is basically going through the entire data set one time. So, and the learning rate LR, the N is the number of samples in our data set. In other words, it's the length of our data set. And X train is the entire training data set. Y train is the entire training set of training labels, right? And so in this particular problem, we're doing the MNIST data. Training is, I think, 50,000 examples, and 50,000 examples, and each example is a digit, is a JPEG of a digit, or not a JPEG, but a matrix representing a digit. And then Y train is 50,000 labels, and the labels are just anywhere. They can be anything from 0 through 9. That's what the digit. That's what the photo of the digit is. All right. So we're going to loop over the epochs. So if epochs is 1, then we're just going to do this once. If epochs is 5, we're going to do this 5 times. And then for each epoch, we're going to divide the data set into batches. And so that's what we're doing here. I is running over the range from 0 to the number of batches. And you calculate the number of batches this way. And the way this is done, and you can test this out and figure it out for yourself, but what it does is it divides the data set into batches of whatever batch size you choose. And the last batch, so every batch but the last has the length batch size. So if I want to divide it into batches of 64, all the batches until the last one have a length of 64 each batch. The last batch is whatever.
Quick question: is this a loop in a loop? Is this a loop in a loop? Okay.
Correct.
Yeah, that was the question. So, thanks.
Yes, that's right. So it's dividing the data set into batches. Each batch is, if you have batch size of 64, each batch will have 64 data points, 64 of these 28 by 28 images in it, right? The last batch will have whatever's left over. So if the number of samples is evenly divisible by 64, then the last batch will have 64 in it. But if not, it's going to have whatever's left. Okay, and 50,000 is not divisible by 64. So in this case, the last batch is going to have is not going to have 64. It's going to have less than 64 samples in it, right? And you can actually try that if you want and see what you got. I didn't actually do that. All right, so all we're doing here is we're giving it the starting index, the starting index of whatever batch we're dealing with, the starting index of the current batch, and the end index of the current batch. And once we have those computed, then we can extract the batch, right? We're just doing this.
Joseph, quick question from the chat. So there came the question came up. So N is 50,000.
Yes, that's correct. That's correct.
Thanks.
Last time I had a problem with participants being stuffed into a wait room, and then they had to be, and only when I noticed I could admit them. And I asked them to fix that, and I think they have. I don't see any participants waiting in. But if somebody sees,
I think we should encourage participants, because there was now this question was asked in the chat. You can just unmute yourself and ask the question. I think that's okay for Joseph, right?
Yes, that's what I was saying. That's what I was saying. Anybody that wants to stop me and has a question, feel free to unmute yourself and jump in. If I find that people are jumping in so much that I can't make any progress, then I'll tell you. But I think right now it's fine. Just jump in and ask your question like Philip is doing. Okay. And if someone monitors if someone could monitor the Slack group, because that way we will see if anybody's having trouble getting into the meeting. And
I can
let me know
monitor the chat and the Slack group. I will do that.
Excellent, thank you, Philip. And let me know if anyone's having trouble getting in or whatever. All right, so here we are. We've just extracted the current batch. The next thing we have to do is calculate the loss function. I wanted to go through in this and actually explain the loss function. I'm not sure we're going to have time to do that, but we've basically adopted as our loss function, since this is a classification problem, we've adopted the cross-entropy loss function, and we're taking that from PyTorch. We actually built this, and earlier in the video, Jeremy actually built the cross-entropy function from the ground up, and then after he built it and demonstrated that it works, he then says, okay, now we're allowed to use PyTorch's version. So if you remember what he did, he imported this this thing from functional. It's called functional, but it has in it all the things, these utility functions like loss functions and so on. And that's what. So then f.cross-entropy is what's being used for the loss function. And that's done outside of this loop. It's somewhere up above. Loss function is being set as that f.cross-entropy function. Okay, so the next thing that happens after we compute the loss function is we do the back propagation to compute all the derivatives, using the chain rule and all that, so that we can then make the updates. And that's what's going on here. Each weight is getting updated, and each bias is getting updated. And then after we do the updates, we zero them out to prepare for the next batch, because we don't want to be accumulating the gradients. There's another little point here, and I think I wrote a note about it. So we loop, I'm going to read what I wrote, the comment. Loop over the layers, applying updates for each parameter. You can see that's what's being done. We temporarily set, by saying with torch.noGrad, we're temporarily setting the requires grad flags to be false. Remember, every tensor has a flag. A tensor is an object in PyTorch, and it has a flag called requires grad, and that flag can be true or false. If it's true, then PyTorch is monitoring everything you do to this tensor, so that it can later on compute the gradient. But when we do the updates, this is a very empirical thing. We're just adding something, a little bit of something to the tensor, and we don't want that to be included in the gradient. We don't want it to be keeping track of that, so that we don't want it to be monitoring that so that it'll make the gradient that much more complicated. So that's why we turn off the flags during the updates. It just temporarily turns them off. That's what with torch.noGrad is doing. It's just temporarily turning off the requires grad flags, making them false during the update process. Okay. Any questions about that? Okay, so that's the thing that we're going to focus on for this entire part of the video. We're just going to focus on refactoring that, making it more and more. We're basically doing software engineering on it. And software engineering, people aren't expected to be software engineers in this class. They're just expected to have a year of coding experience. So that's why this part is really dense, because Jeremy's a really good software engineer, and he doesn't mind showing it. So we're all seeing all this great stuff that he and Sylvain Guger are doing, and so I thought it's worth taking time to see exactly what's going on. So I'm going to do that. Okay, so the first thing he does is he refactors it. This is weird because he goes through this refactoring, but then he undoes it and goes back to the old way. But this is the original version of model, and it inherits from the class nn.module, which is a special class in PyTorch that has a bunch of innate features. So a layer is a module by this definition, and the input for this class model is a list of module objects. that is these layers. And remember, he built these layers, the linear layer, we talked about this last time, the Relu layer, and the second linear layer. And I've just changed the input number, the input descriptions to be more descriptive. That n in is the number of inputs. The n hidden is the hidden layer, the dimension of the hidden layer, which is 50, the way he's chosen it. Then there's this Relu function, and then the second linear layer takes as its input the number of hidden, the 50 element hidden space, and then as its output, it takes it gives an output of 10 activations. All right, so when you call this function, it loops through the layers and sequentially, recursively applies them one on the other, right? So as you can see, this is going to loop through the layers. The first is going to be the first linear layer. So x equals the linear layer of the linear layer of x. You're going to replace x now with the linear layer applied to x. Then when it takes its next value, it's going to apply the Relu to that. And then x is going to be the output of Relu operating on linear, operating on input. And then the final value of L is it's going to take this value, the second linear layer, and then x is now going to be linear layer 2 operating on Relu, operating on linear layer 1, operating on the input data. And then that's what it's going to return as the output. So the first thing he does is he refactors this thing to eliminate this loop here. He just explicitly calls it, you know, just like I said, linear layer 1 operating on the input, and then Relu operating on that, and then linear layer 2 operating on the result of that. So it's funny how he does this. It's just, it shows you that these classes are so very plastic. You can change them at will and make them do different things. But then he goes back on it and says, okay, well, let's go back to the original way. So I guess that's what happens next. So then he refactors this. It's really the same thing, but now he calls it dummyModule instead of model. But he's doing it. He's now saying, okay, let's try to do this without using PyTorch. Because remember, the previous version of model, we had to use PyTorch's nn.module. That's a class in PyTorch. So now he's starting from the ground up. No, it does not inherit from a parent class. So he initializes it with, one of the things that nn.module does for you is it keeps track of a module dictionary. So he builds that module dictionary here, self.modules, self._modules. And then he populates it with the linear models, the linear modules. And I guess he doesn't need Relu because Relu doesn't take any inputs. So then this part, I must say this is a little strange to me, this syntax, but it looks like he's looping over the dictionary, and let's see, it's not, and self.modules dictionary 1. Yeah, and he's basically adding each of these input elements to this dictionary. So he initially populates the dictionary. It's not populated, it's just an empty dictionary. And this loop, he's populating the dictionary with all of the, whatever he found in the inputs. And then he returns the module dictionary. And then the other thing that nn.modules does is it keeps a parameters list for you. Parameters meaning the weights and the biases. So now he's defining this parameters list for L in modules, for P in L.parameters. There is one basic unit that we're using, and that is this nn. Whatever it is here, nn. This thing, we're actually using this from PyTorch, and it implicitly has an attribute called parameters. So we're basically just looping over each module and collecting all the parameters. And you can see why we didn't include the Relu among the modules, because the Relu has no parameters. That's why we didn't include it. So now we build this model using dummyModule. So remember, this is an abstract class. Nothing is going on. You know, this is just a sort of a pattern or a template for building something. and it tells you what properties this object is going to have. Now we're actually going to what's called instantiating the class. MDL is an instance of this class now. We've actually given it the inputs that we want, and it's now an object that we can then do stuff with. And then if you look at the object, you can see it has a dictionary. That's what these brackets are. It's a dictionary consisting of L1. Entry L1 has linear, is the first linear module, and L2 is the second linear module. And the input size is 784, which remember is 28 by 28. So 28 times 28, that's flattening out this 28 by 28 array that holds the digit, that holds the JPEG or the photograph of the digit. Okay, so is everybody up with me here?
I have a question, Joseph, in the
yes,
comments.
sure.
In line, it's claimed where the comments say loop over self modules. Yeah, exactly that one. Registering each as parameters. I don't understand how that is a loop, because it's just a logical statement that asks sort of, if not this condition is met, then equals to v, then do super whatever. Where's the loop in that? Is that maybe a mistake in the comment, or what's going on there?
It might. I have to admit that this particular line, I don't quite understand what it's doing, but I think that's what it's doing, is it's populating that dictionary.
Yeah, that's right, Joseph. The only difference is that it's a loop because set attribute is called every time you basically initialize something in init.
Yes.
So that's why. Right. Yeah. So that's why you even have that condition that underscore modules is also being initted. So you don't want set attribute called on that.
That's right. The underscore modules are generally considered private to the class, so we don't want to export them in this module dictionary. So yeah, so people who are much more experienced with Python will understand this better than I do, and thank you for that explanation. So it is a loop, and it's basically populating the modules dictionary with everything it finds in the inputs. Every object that it finds in the inputs.
Yes, thank you very much. So we can indeed call it a loop.
Yes.
Yeah,
yes.
yeah.
Okay. So then he talks about registering modules, and as if everybody understands what that is. It's not so clear, but you can look it up, and I looked it up, and what it is it's, let's see, PyTorch has this internal, the way this module operates internally is it has this collection of parameters. For each module, it keeps a collection of parameters. So when you register a module, that tells it, okay, keep track of these parameters for later use. So so this is what I wrote here. This is what Jeremy wrote. We can use the original layers approach, but we have to register the modules. And so now I'm trying to explain what he meant by registering the modules. And when he says the original layers approach, now he's going back to looping over the, let's see, yes, he's going back to the loop over the layers. So this is a little confusing because he refactored it once to eliminate the loop. Now he's going back to the loop. But that's okay. We can follow what he's doing. When a module is registered, that means that it's added as an attribute of the class so that its weights and biases are now incorporated as module parameters. Remember, the nn.module has that internal structure that it's looking for attributes, and each attribute has parameters. So it's internally and automatically building up a list of parameters that you can then get to later on when you need to do the updates. All right, so that's what he means by registering. It means that we have to add the module as an attribute of the class. And let's see, where's that happening? So it's happening right here. He's looping over the layers, and for each layer he's adding it as a module. And this this F string structure might be unfamiliar to some people. Let me just check if everybody can still hear me. Can people still hear me?
Yes, I can still hear you.
Thank you. Thank you so much. Okay, so this F string structure, F and then quotes, what it's doing is at execution time, it populates this, whatever's in these brackets. So in this case, it's I, and I is the index of the layer. So it's going to loop through the layers, and when it actually executes, it's going to self.add module of let's see, layer 1 or layer 0, sorry, and L being the layer. So add module takes an input of a string and an actual layer object, and that's what this is. That's what this F string is doing. It's giving you that string to describe the layer. You see, as it loops through, I goes from 0 to 2 or something. Let's see, because we just have these. Oh, we have 3 layers in this one. So I is going from 0 to 2, looping through the 3 layers, and we can see what happens the first time. I is 0, L is NN linear. It's the first linear layer. So self.add module, it's going to take the string, which is going to be layer underscore 0, and it's going to take the object L, which is going to be NN.linear, the first linear layer. Does everybody see that? And then the next is I equals 1 and L equals the Relu layer. And so it's going to register each of these modules sequentially. And this add module is an internal functionality of NN.module. And that's why we haven't seen it before. Okay, so now with this new version of the model, we can now instantiate the model the same way. The input is the layers that is a list of layers, and here it is, the list of these 3 layers. We supply that list as an input to this new class model, and then we instantiate it, and then we have this model. And then if we look at what's in the model by just writing model, it'll show us layer underscore 0 is going to be the first linear layer, layer underscore 1 is the Relu, layer underscore 2 is the second linear layer. So does everybody see how that works? Okay.
Yeah.
I kind of half see it. I mean, I kind of understand it. One of the things I was wondering is, remember when Jeremy presented, he said people always asking, where does that number come from? And he said, you tell me, is it a parameter or an activation? Parameters are the same as weights, correct?
Weights or biases, right?
Okay, that was really my question, because I was trying to think how biases fit in. So biases is a synonym here for weights?
No, remember when he does the matrix transformation, it's WX plus B, where B is a column vector.
Yeah.
W is a matrix. So W is the matrix of weights, and B is a column of biases. So these are parameters that need to be, these are the weights and the biases are all the parameters. A lot of times when Jeremy goes through this, he ignores the biases just because it's easier to explain without paying attention to the biases. But we do have to pay attention to the biases, right?
Yep. Okay. Thanks.
So okay, next.
Joseph, in this case, we do have the biases, right? They're kind of hidden in NN linear.
Yes, that's right. That's right. NN linear. I didn't start at the beginning of this of the code because we went over much of it last time. And NN linear is where you define that layer, and the inputs are the weights and the biases. And remember, last time we discussed how to initialize those weights and biases. Oh, actually, we didn't talk much about biases. We just said we initialized those to 0, and we were much more worried about the weights. All right. So now that we've built the functionality of module list, we now get to use the PyTorch version of it, and that makes our model. Now he calls it sequential model. It's basically refactoring that model class that we already had, and now he calls it sequential model. And so you get this, you go through the layers and you use the functionality of this internal method of nn.module called nn.module list. So this does all the registering and so on. It registers the parameters and so on. And again, the call is just looping over the layers. Now he's going back to the loop instead of explicitly calling out each layer. Okay, and then here's what it looks like when you instantiate it, and here's what it looks like when you ask what's inside it. And no, we can actually set bias equals false if we want to do without biases. So this module object has as its inputs, you give it the number of features from the input, and the number of features in the input, the number of features in the output, and this bias flag, whether it's true or false, whether you want to use biases. And as far as I know, we always want to use biases. So we set the bias flag is by default set to be true. And here's what it looks like, and this is exactly the same output that we got when we looked at our homemade version of model. So now, so what he's doing is he's building things from scratch, but as we get to each point, we now as we've duplicated each functionality inside of PyTorch, we now get to use PyTorch. So that's what we're doing here. All right, what did I just do? Use PyTorch nn module list, and now there's this internal functionality in PyTorch called nn sequential. And let's see. Oh, I'm sorry. At the bottom, nn sequential unit class. Oh, I skipped a page maybe. Let's see. Go up. Module list. Sequential model. Okay. And then so we get to use PyTorch nn.module list and nn sequential. What are we doing here?
If you go back, Joseph, in nn module, you have defined dunder call, and nn sequential kind of makes nn call to be replaced.
That's right. It calls the modules recursively one upon the other. So that's the new function. That's the functionality that we had already built from scratch, but now, see. I'm not sure what we're doing here. We already. This is instantiating the model using the new class that we built, and then this is executing the training loop. We've seen how this works. There's this fit function that we've built, and that's basically running the model. And then we compute the loss function, and then we compute the accuracy. Once we've built the model, we can do those things. This is basically a forward pass. And so I'm not sure what I meant by this, what I meant to explain here, but I'm just gonna go on. Okay, the next thing he does is he creates this optimizer class to do all the updating. Remember, he already did the updates sort of by hand. He built that, and now he's going to try to make it a little bit nicer. So we have this part of the loop with torch.noGrad for p in model parameters. You update the parameters with with stochastic gradient descent. So now he wants to build something that will instead just be called whatever functionality is here is going to be taken care of by these two things. He wants to build a class that will do these things. And so that's what we're doing here. What optimizer does is it takes the parameters and the learning rate, and then it actually executes the same thing that we built above. It loops through all the parameters that are registered in the model. It updates them with the gradients that it calculated in the backpropagation step, and then it zeroes out the gradients to prepare for the next batch. Right. So now here's what it looks like: model equals nn.sequential, and that's what we did before. That's the call from before. But now we do the second thing. We instantiate an optimizer, which we call opt. So we built this class called optimizer that basically takes care of updating the parameters and zeroing out the gradients. That's all we've done here. All right, now.
Sorry, Joseph, just one question. Back to that optimizer
Yes.
thingy, your previous
Yes.
page.
Yes. I'm here now, right?
No, I think it's the next
Hello?
page.
Oh, the next page down?
The next, yeah. Oh, no, sorry, no.
Back. Optimizer, there it is. Oh, sorry,
No, the
more
one
up.
where you had yeah,
There it is.
that's the one. Yeah, great.
This is it. Uh-huh.
Sorry, so it's been a while since I looked at this. Just a quick question. You know, when you say so for parameters for P and self parameters, that's both the weights and the biases, or is it just the weights?
It's the weights and the biases. See, the nn.module collects all the parameters. It knows, you know, it looks at the inputs, it looks at the input modules, and it sees whether they have weights and biases or just weights. And whatever the case is, it keeps track of all those parameters. It adds them to its list of parameters. This is all done under the hood. You don't see it. But it's basically collecting a list of parameters, and it knows which module each of these parameters is associated with. So now we've got 3 models. You know, the first linear model, the Relu, which has no parameters, and the second linear module. And it collects all the parameters. Now, Relu has no parameters, so it's basically collecting all the parameters from the first linear layer, L1, and from the second linear layer, L2. And it knows the difference. It knows that this, you know, when you loop through parameters, it's looping through all the parameters from all the modules. But it knows which parameter, it knows which module the parameter is from, so that when it does the back propagation step, it knows the right way to compute the chain rule, the derivatives in the chain rule, the gradients. Does that make sense?
Yeah, okay. And just one other question, and I'm sure that this has been covered before. So if someone has a link, that would be really handy. And the question is more around why does the change in your parameters need to be, you know, P is minus equals P grad times the learning rate. I know that that's what it is, but if someone has a good explanation or short explanation of why it is exactly that and not something else, that would be quite handy. So thank you.
Okay, well, I'll give you an initial short explanation. That is stochastic gradient descent. That's exactly what this stochastic gradient descent is. It's going to compute the derivative and the negative derivative. Remember, the negative derivative tells you the direction towards the minimum, and then it's going to multiply that by this multiplier called the learning rate. So that learning rate decides how big the step is going to be, but the gradient decides what direction the step is going to be in. Does that make sense?
Okay, and then you do it. Okay, fine. Yeah, fine. I'll have to think about it a bit longer because I recognize.
Yeah. So the link. So the link to look up. The link to look up is stochastic gradient descent, because this is just implementing that.
Great. Okay. Thank you.
Great. Okay. So after we built this optimizer, now we
just one quick thing, returning to the difference between the module list and the sequential, those two choices. I think the one quick note that he made was that the sequential performed better just because it's stacked and it can be done simultaneously. And there's just different times when you'd want to use one versus the other.
Oh, okay, I didn't remember that from his lecture. So you're talking about the 2 different ways that he refactored model, and one way is he's basically looping through the layers and applying them that way, and the other way is he's basically calling out the models all in one line. And I can see that the benefits of both. If you just have a few things to do, if you just have these 3 layers, then it makes sense just to call out the layers so that you see exactly what's going on. But a lot of these models that we will see in the future, and we maybe we already saw them, have tremendous numbers of layers in them, and then it would make more sense to loop over the layers instead of having to call them out all in one line. So is that what you're saying?
That's right. I just put a link in the chat that there's a really nice Git that kind of compares the two, but that's right.
Excellent, thank you. All right, okay, so now that we've created the optimizer class. We get to use it we will use it in our model and in our fit function. And so here's that refactoring. You can see what's going on. We are remember, this is the same fit function that we started with. We're looping over the epochs. We're looping over the batches. We're getting the current batch. We're running the model on that batch, which gives us the predictions. We're running the loss function on that batch, which calculates a number for the loss function. This is the forward pass. Okay. Then we do the back propagation. Then we apply the corrections to each of the parameters. That's what this is doing. Then we finally zero out the gradient. So this is what it looks like when you train the model for one epoch. You just do fit, and then loss and accuracy are computed once the model is they take the model as the input, right? And they take the XB is the data from the batch, and YB is the labels from the batch, and the same thing. And then accuracy compares the model predictions with the actual labels and decides what fraction is correct, something like that. And you can see here the output. The loss function is 0.128, and the accuracy is 97% roughly. Okay, so now that we've built this functionality, we now get to use the internal PyTorch version, which is optim.sgd. SGD stands for stochastic gradient descent. And SGD has other features like momentum, and we've seen that earlier in the first course. And it has bells and whistles that can make the parameter update process better and better and better. So it now makes sense to use the SGD. All right. Sorry, I mean, we use PyTorch's internal version, and that's what we're doing here. Get model, return the model, and the optim.sgd of the model. SGD operates on the model parameters and given the learning rate. So now this is what it looks like to instantiate the model, compute the loss function, and train. So I'm going to go further. Next, he adds this dataset class, which makes so the next part is focused on loading the data. We've already got the internals of the fit function all set. Now he wants to make the data loading process nicer. So he first defines this dataset class, and all it does is it puts together the training examples and their labels into an output. So here's the raw data. XB is just the raw training data for a batch, and YB is just the labels that correspond to that data for that batch. And now he wants to introduce this class that will give us a tuple consisting of the data and its labels, and that's all this class is doing. And so dataset has these parameters called X and Y. So if you instantiate dataset, giving it the training data, the training labels, and the validation data, the validation labels, you then train ds is now a tuple consisting of the training data for that batch and the labels for that batch. Valid_ds is now a tuple consisting of the validation data for that batch and the validation, the labels corresponding to that batch. Okay, and these assert functions are just showing us that I didn't actually execute them. They're just showing us that these things behave as we expect them to. So he built this simple dataset class. Next, he's going to refactor the model to use the dataset class. And let me go up one because there's something, let's see. Oops, I went down one instead of up one. There's the dataset class. Yeah, so you can see what he's doing. He's just grabbing a batch. This is the starting index of the index of the first element of the batch, the first sample in the batch, and this is the one more than the index of the last sample in the batch. So you can see what he's doing is he's taking a slice of the data that is giving us a batch, and the batch is organized in a tuple of data and labels. That's what he's doing here. Okay, so next he's going to refactor this model function to use the new functionality that we just built. So xb, yb, so he's going to grab a batch, he's going to specify the start and well, for each batch, let's say, he's going to grab the batch and he's going to do the predictions, he's going to calculate the loss function, he's going to do the back propagation, then he's going to do the parameter updates and zeroing out the gradients. So now he's got this whole thing, this fit function is now much more compact than he had it before using the new functionality. And so then he's just going to continue and make things even more interesting. He's going to add this dataloader class. So he wants to, so dataloader is going to be this iterator that actually grabs you a batch when you ask it. It yields the next batch for you. So the inputs are this data set thing that he created and a batch size. And then he builds this iterator that yields the next batch. So now you instantiate this data loader class, and trainDL is now a data loader object. And this is how you actually use it. You iterate, and then you ask for the next element of it, and that's what an iterator does. You can ask for the next element, and then these assert commands are just showing us that the XB part is indeed the data part of it, and the YB part is indeed just the labels. Okay. So now he's going to refactor this fit function now using the data loader class, and it's doing the same thing as the long version that we started with, but now it's just a more compact and easy to understand way. He's basically isolated all the steps here and all the steps that you expect. So we're looping over epochs, we're looping over batches. This just the first line here for XB, YB in trainDL, that just iterates over and grabs the next batch for you as you loop over that. You do the prediction, you calculate the loss function, you calculate the gradients, you apply the step to do the updates of the parameters, and then you zero out the gradients. So that's what this part is doing. The next thing he wants to do is add a feature, add a functionality, so that instead of just taking the samples as they come, you want to be able to grab random samples. So he built this thing called a sampler. It's a class called sampler, and what it does is it just outputs the indexes of a random permutation of this of the size of your batch. So what comes in is the whole data set, the batch size, and whether you want it to shuffle or not. Because you can call sampler, and he's building in this functionality that if you want it to, it'll give you a random sample, but if you turn shuffle equal false, if you put it to false, then it's just going to give you a sequential sample. And so that's what it's going to do here. If self.shuffle is, well, self.idx's, that's the indexes that are going to index the samples in the batch, are going to be a random permutation of the number, the input number. The .n is 50,000, right? It's the length of the whole data set. It's going to be a random permutation of that. If shuffle is on, otherwise it's just going to be the whole data set in its original order. You see what that does? That's what this line does. If you want a randomly shuffled batch, I'll give you one. Otherwise, I'll just give you the whole. Sorry, if you want the randomly shuffled data set, I'll give it to you. Otherwise, I'll just give you the whole data set as it was. I won't do anything, in other words. And then next, he samples from this set of indices and gives you the indices for a batch. So the input now is the batch size, and he's going through from zero. He's stepping through the data set by batches. That's what he's doing here. Remember, this is the initial index, this is the last index, and this is the step size as you're iterating through. That's what this range command does, remember? And so he's going to, this is an iterator, then it's just going to yield the set of indexes that will, the set of indexes, whether random or not, that will be for the next batch. So then this is how you use it, small ds. He's building a small data set. He's just going to use the first 10 samples, right? So data set star train ds means, the star means go through, remember train ds is a tuple that has 2 elements in it. So star train ds means the inputs should be both of the elements of train ds. That is the samples and their labels. All right, so that's what he's done here. Let's see. Oh, we haven't used the sampler yet, so that's what happens next. Sorry. So first he builds this data set. Then he uses the sampler class. S equals sampler of small ds. That's the input data. We want to sample with a batch size of 3. I think that's what we want, right? Let me just make sure. Sampler takes a batch size, right, as second input. So we're doing this little experiment. We're taking a small data set of length 10. The batch size is 3, and at first we're not going to shuffle the data. And so remember, S is now an iterator, so we can go through all the elements of S and see what we got. And so here's the 3 batches. We have the first 3 elements, the next 3 elements, the third 3 elements, and then remember there's a leftover because 10 isn't equally divisible by 3, isn't commensurate with 3. So the leftover batch has just 1 element in it. This is an illustration of that. Okay, now we're going to go through and see what it looks like when we tell it to, yes, do randomize it. So now we go through and do the same thing, and we see now we get random, just random. Each batch is randomly chosen from the whole data set, and there's no repetition, right? Because that's what this rand perm does. It gives you permutations, but it makes sure that the permutations are not repeating. They don't repeat any elements. So now you can see these are randomly shuffled, and then if we ask for the next one, it gives us another different batch. You see, different indices from the data. So that's what this sampler does. Okay, so now he resamples this dataloader object to use sampler. So inside of it, instead of just iterating over batches as they come, he's going to sample random batches. Now this part is a little complicated, so I went over it a little bit more. Let's see. So the things we have to understand are, what does this collate function do? And so let's try that first. So the first thing is he builds a training sample, and we want to shuffle. When you build the validation sample, you don't want to shuffle because you're not, you don't need to shuffle. So that's what's going on here. And then once you've made the sample, you can now build the sorry, this is not a sample, this is a sampler, which means that every time you call it, it gives you a random sample. It's one of these data loader objects. I'm sorry, it is not a data loader object. It is an iterator that generates a set of indices that index the elements in your batch. So train samp itself, if you look at it, it's just a bunch of indices. And so that's what this data loader takes the train data set, and then it takes the indices that select out the batch. And then it also takes as its input this collate function. And then when you call it for the validation, you do the same thing. And remember, the validation sampler doesn't shuffle, okay? But now let's go look inside this thing. What happens inside data loader? First,
Joseph, quick question.
Yes. Yes.
Yeah. Can you just, so the data, data, what is it? I'm trying to get to what is a given image submitted in order to be, for us to figure out. that is a what? That is a data. Is the data
that's
bunch?
A sample. That's a sample. Yeah, that's just, remember, it's a flattened version of the image, of the 28 by 28 image. So each sample is a 700, it's basically a vector of length 728, and then it has a corresponding label, which is a single number from 0 to 10. Does that make sense? 0 to 9.
Okay.
Sorry. Does that make sense? Okay. So yeah, I know it's really hard to hold all this stuff in your head. So that's why I'm trying to take it apart. What happens inside of dataloader? There's this thing called zipstar. There's a command called zip of star small ds. So let's look at that inside of dataloader. See right here, zip, and B. The B is the batch. Okay. And so that's actually, or maybe it's the whole sample. No, it's a batch. So I've made a comment here. It returns an iterator for the input B, which is a batch data set composed of a tuple of X and Y, where X is, as I was saying before, it's this vector of length 728 corresponding to the image, and Y is the single number corresponding to the image, to the label. And so the batch is a whole set of these. There's a whole set of each row has the 728 vector and a length 1 label, and a batch consists of whatever the batch size is, number of rows. So 64 rows if you want the batch size to be 64. All right, so let's go.
Why do you have to return a stack, Joseph?
That's what I'm getting into here. That's what I want to do that in the next. Whoops. And what happens inside dataloader thing. So first we're going to look at what happens when you do this zip function and you input this small ds. Remember, small ds is 10 samples and their labels. That's what we made this. We built this before. Star small ds means include the, small ds is a tuple, and it has the first element is the data and the second element is the labels. So the star says include both elements, include all of the elements of this tuple. And the zip returns them it returns the x's and y's of a batch in tuples of tensors. So xs is a tuple of tensors, and each one of them is an input, right? This 784 vector. And ys is a tuple of the labels. So look what happens. We print the lengths. They're 10. We know that the x's. We know that there are 10 elements in this little sample ds that we built, and so it's telling us the length of. I should have put shape, and then you would see that it's 780. The xs is 784 by 10, or 10 by 784. What type is it? It's a tuple. That is, xs is a tuple, and it consists. And then if you print, I don't want to print xs because remember xs has all of these vectors in them. But I'll just print the y so that we can see them. What do we expect them to be? We expect them to be a tuple with the labels of these 10 examples in this batch. And so here they are. It's a tuple with all the labels in it. Now, why do we stack them? John asked, why do we stack them? Well, because that puts them all into a tensor. So xxyy equals collate of small ds. Remember what collate does is it stacks the tuples into a single tensor. So len of xx and len of yy are still the same, but the type now is a tensor. And if you print yy, you get a single tensor with all the labels in it, as opposed to separate tensors for each label. So you see it's stacking. Stack is an appropriate word here. It's stacking all of these individual tensors into a single tensor, and it does the same thing for the input for the examples. For the input images, it stacks them into tensors. Okay, so that takes us inside of dataloader. We see what's going on in there. Now, how do you use dataloader? Well, first you get your sampler, and remember, train samp is just going to give us a bunch of indices that are going to. It's remember it's an iterator, and every time you call it, it's going to give you a bunch of indices. In this case, it's going to be 64 indices because batch size is 64 that correspond to the next batch. So it's just a list of indices, okay? But then when you input it into dataloader as the sampler variable, that tells dataloader which samples to pull out into the batch to make that batch. So what it does is it goes through every time you call it and pulls out a batch from a random. If you told it to pull out a random batch, it'll pull out a random batch. Otherwise, it'll pull out the next batch. So here we go. We first build a trained data loader, and remember this actually does randomly sample, and then we build a valid data loader which doesn't randomly sample. It just takes the samples sequentially. All right. So here's how you use the data loader. The same structure we saw before. Next iter, it basically pulls out the next batch, and if we want to see what that batch looks like, we can do imshow of xb0. That's basically the image, and .view 2828 means put it into a 28 by 28, 28 by 20. In other words, remember that xb of 0 is a 784 length vector. So .view says like rearrange it into a 20. Yeah, reshape it into a 28 by 28 array, and then we plot it, and then that's what it looks like. And YB of 0, that's the label that we got, is 3. Okay, but now just to show that it's actually randomly sampling, we next look at the next sample and pull out the next sample. You can see it's also a 3, but it's not the same 3. It's a different 3. It just happened that the next sample in the random batch was a 3, but it wasn't the same 3. And then call it again, and this time the next batch turns out to correspond to a 6. Okay. All right, and actually the batch has 64 elements in it, right? We're just choosing the first one. So if I would have chosen XB of 1, I would see something else. And YB of 1 is the label. It corresponds to that new image. So far, is everybody up with me? This is basically drawing a random batch for us. Okay. Now we can put it together. PyTorch has its own data loader, and that's what we're doing here. We're importing it. Remember, we're importing, now that we've built a data loader, we know what it does, we can use PyTorch's internal data loader, and there it is. And I think I'm at the end here. I don't have too much more. I want to leave so that you can, I have a few more. We're basically done. This is the refactored pipeline, and you can see how he's got it in 3 lines. I mean, sample the next batch, or this is our build the data loaders, then get the model, and then compute the loss function and the accuracy. It's in 3 lines. That's our whole pipeline. And so this is kind of really cool. And this is software engineering. So now you're learning how to become software engineers, and so am I. So I'm learning along with you. So, and now he's finished it, so he exports it for the next notebook. Now I'm going to leave abruptly, and so everybody who wants to can go to the next meeting. I'll stick around a little bit because now that we have parallel meetings, we have the capability of setting up parallel Zoom meetings. I don't have to leave. So anybody that wants to ask any more questions, or if we want to go through the rest of the last few slides with me, I'm here to do that. Any questions? Oops.
I'd just like to take the opportunity to thank you, Joseph. It was very enlightening today. As you said, a lot of software engineering stuff. So thank you, yeah.
Yeah, thanks,
Joseph. Oh, you're welcome. So you're welcome, John. I'm going to put this slides on the Slack group so that people can see them. And I only missed, there was only like 2 or 3 slides left. So, you know, we basically got through the whole part what I wanted to get through today. And next time we'll hopefully cover the callbacks, and hopefully we'll cover it in one lecture. So we'll see how that goes.
Thanks a lot.
Oh, you're welcome. and we'll see you next time if there are no other questions. I'll stick around for a few minutes anyway. Okay, well, there are still 7 of us here. Yes. Sorry, did you want to say something? Does somebody have something they wanted to say?
No, just wanted to thank you, Joseph, for today's meeting. Okay.
Well, since there's a few people still left, I assume they want to go through the last few slides with me, so I'm just going to do that. There's only like a few more slides to go. So here's we did this. Oh wait, no, we didn't. Where were we? We were right here. So now we're going to use the data loader that we built, and we're going to draw this. We've used PyTorch to build the data loader now from its internal version of data loader, and it also has this random sampler thing that does the same functionality as our sampler. So the data loader, remember, takes as its input. You have to specify what the sampler function is, and you have to specify what the collate function is. We built that functionality into our data loader because PyTorch's data loader has the same. So now that we've built a data loader, we get to use PyTorch's internal data loader, and that's what's going on here. We imported it. So now, since we imported this from PyTorch, now when we call data loader, we're using PyTorch's internal version instead of the thing that we built in the last few frames. All right, so now we draw a random batch using the same way, using PyTorch's data loader for the training. And then this is how the model looks. I think he built a function above. I didn't go into it much, but it's just a simple function that builds the model. I'm not sure. It might be reflected in one of the previous slides. And then we have this fit function that we have been refactoring the hell out of. And then, so this is we run the fit, we get the loss function, and we get the accuracy, and that's the whole training loop. So now he refactors fit to make it even nicer, so that it knows how to handle the case of the training or the case of the validation, in which case all you want is predictions. Remember, when you're training, you want to be adjusting all the weights and biases using stochastic gradient descent. But when you're running on the validation set, all you want is predictions. So that's what he's done. He's put those dual functionality in there, and he has what do you call this? An attribute or a function called train. He builds into this fit function an attribute called train, which does this thing. It loops through the data and adjusts calculates the loss function, does the back propagation, adjusts the weights and biases, zeroes out the gradients, just like we saw before. But now he builds this inference phase. So first they have a training phase. And the reason why he did that is because in the future we're going to build in functionality of batch norm and dropout, the extra functionality that we're going to build in our future work. And then the inference phase is simple. It's just evaluating the model. And here you're just looping through without randomly shuffling the batches. And we're just going to do the prediction. We're going to get the loss function. We're going to get the we're going to accumulate the loss function. We're going to accumulate the accuracy. And NV is the number of validation is the number of batches in the validation data loader. and then we're going to print the epoch, the total loss, which since we've accumulated it, we have to divide by the number of examples to get the loss per example. And the same thing with the accuracy. We're accumulating the accuracy each time we do a batch, so now we divide by the number of batches. And then we return the average loss and the average accuracy. So that's our new fit function. And then finally, the whole pipeline, this is the last slide, he has this function called get data loaders, which basically takes these data sets that we built. Remember we had this data set method and a train DS, remember, is a tuple of training examples and training labels. And valid underscore DS is a tuple consisting of the validation examples and the validation labels. Okay, and batch size is batch size, and star KW args, I'm not sure what that is right now. So it returns, so I guess there's optional arguments that you build in that just get passed into the data loader. I guess data loader can take extra arguments that, remember, we're dealing with PyTorch's internal data loader, and it has methods of doing batch norm and dropout and so on. And I'm imagining that that's what these keyword arguments are controlling, that process. We don't have that in our current loop, so KW args is going to be empty right now. All right, so return data loader. Okay, so what it's doing is it's taking in the training data set, the validation data set, and it's outputting a training data loader and a validation data loader. And remember, for the training data loader, we want shuffle to be true. We want randomized sampling, but for the validation set, we don't need to randomly sample. And the other thing he does, the little tricky thing he does here, is he doubles the batch size for the data loader, for the validation data loader. And the reason he can get away with that is because you don't have to carry on all the extra baggage of the back propagation and so on, the gradients and all that. So you now have more room in memory. The batches are smaller, so that's why he doubles the batch size. It's just a little trick that he's using. All right, so now he makes the data loaders by calling getDLs. Remember, the DS, these are just the data sets and then the batch size, so that's all you need as the inputs. Then you instantiate the model and the optimizer. That's all this function getModel does. We haven't really looked at it, but all it is instantiating the model and instantiating the optimizer, both of which we've seen before. And it might be in one of the previous slides that I didn't really talk to it, but that's okay. You can go through that. Okay, then we run the model for 5 epochs. So now that's just this. We give fit the inputs that it needs, which is the number of epochs, the model that we built, the loss function that we built or that we're specifying, the optimizer that we specified, and the data loaders, the 2 data loaders, one for the training set and one for the validation set. And this just asserts that the accuracy is bigger than 90%. So in other words, that everything's working. If you wanted to, you could actually see what these numbers are exactly, but we didn't do that here. And then finally, he exports everything so that it can be used in the following notebooks. And that's it. All right. So are there any other questions? Because if there aren't, we can just end the meeting. All right. Well, thank you all, and we'll see you next time. We'll talk about the callbacks. All right. Have a good weekend. Bye.